All right, so this is the second part of today's lecture, and we are covering section 2.6 of your book, Cartesian vectors and their addition and subtraction. The objectives of today's this lecture represent a 3D vector in a Cartesian coordinate system, right? And find the magnitude and coordinate angles of a 3D vector. Add force vectors in 3D space. So if you remember, what we did earlier was all in 2D space, x and y. But now we are going to learn about Cartesian vectors and their addition and subtraction in 3D space, right? So 3D space is x, y, and z space. All right, so let's move forward. Let's talk about Cartesian unit vector. Okay, so we already know what is a unit vector. Unit vector is a vector with a magnitude of 1. It has no units, right? And it gives you the direction of the vector. Okay, so it only gives us the direction. So for a vector A, let's say we have a vector A with a magnitude of A. So the unit vector is defined as this guy, u sub A, right? So unit vector is u sub A. And how do we get unit vector? We divide the vector A divided by the magnitude of vector A. All right, so vector A divided by the magnitude of vector A will give us the unit vector A, or u sub A, which gives us the direction of vector A. What are the characteristics of unit vector? We already talked about that its magnitude is 1. So there is no magnitude, right? It's a unity. So that's why we call it a unit vector, right? It is dimensionless. It has no units, right? And then it points in the same direction as the original vector A, right? So all these are characteristics of a unit vector, which gives us the direction of the original vector. Let's say u sub A is the unit vector of vector A, okay? All right, so in the Cartesian coordinate system, or Cartesian system, we have I, j, and k, which are the unit vectors or direction vectors along the positive x, y, and z axes respectively. Okay, so let's say if we have this 3D system with y-axis, z-axis, and x-axis, right? So this vector I, or unit vector I, gives us the direction of x-axis, right? This unit vector j gives us the direction of y-axis, positive y-axis. And this unit vector k gives us the direction of the z-axis, positive z-axis, right? So that's how we denote these I, j, and k in terms of x, y, and z-axis, right? So just remember that here we are talking about 3D space or 3-dimensional space, right? In the previous part, we discussed about 2D space, right? So now we are doing everything according to 3D space. Okay. All right. Cartesian vector representation. Okay. So let's see here in this figure. Let's say this is a 3D box, right? So this is a 3D box with the sides AX, AY, and AZ meters long, right? So this is your x-axis, this is your y-axis, this is your z-axis, right? Because this is a 3D system, so we have these three coordinate axes, x, y, and z axis in 3 different directions, right? Now, this box has a sides of ax, a sub y, and a sub z, right? So this is a sub y along y-axis, this is a sub z along z-axis, and this is a sub x along x-axis. So these are the 3 sides of this box along x, y, and z-axis, right? So these are the sides. Now let's move forward. Now we have a vector A shown in blue color, right? So this is your vector A, right? So this is vector A, and this vector A can be defined as AXI plus AYJ plus AZK, right? So as we are talking about 3D space, so we have three components, AX, AY, and AZ, right? So how do we write this vector A? We write it in this fashion. Vector A equals AXI plus AYJ plus AZK, right? And meters, of course, you don't have to forget about the units. So as we're talking about the length here, so it's meters. All right, so let's move forward. Now, let's talk about the projection of vector A in the XY plane, right? So this is your A dash, which is the projection of vector A in the XY plane, right? So if we take that projection of vector A in the XY plane, let's call it A dash. Now, if you want to find out the magnitude of A dash, so if you look at this gray triangle, this guy, this triangle, so A dash equals AX squared plus AY squared whole square root, right? That's how you find this A dash, right? So A dash equals AX squared plus AY squared whole square root. Same approach as a 2D vector, right? So that's how you find A dash. Now the magnitude of the vector A can be obtained as here, right? So what is the magnitude of position vector A? A equals A dash square plus AZ square whole square root, right? And we can also write that as this guy, if you just put in the value of A dash. If you put in the value of A dash, then this is your vector A. This is, or the magnitude of vector A, right? So AX squared plus AY squared plus AZ squared whole square root. So this is, if you remember, we did the same in the 2D system, right? In the 2D system, we only had AX squared plus AY squared whole square root. But here, as we are talking about 3D system, so we have three components, AX, AY, and AZ. So how do we find the magnitude here? We just add AZ squared, right? So the magnitude of vector A is this guy, which is AX squared plus AY squared plus AZ squared whole square root. Okay. All right. Let's move forward. Direction of a Cartesian vector. Let's talk about the directions. The direction or orientation of vector A is defined by angle alpha, beta, and gamma. Right? These angles are measured between the vector and the positive x, y, and z axis. Right? Their range of values are from 0 to 180 degrees. Now again, if you look at that 3D box, so this is your, and the blue color, you have this vector A, right? Now this vector A is making some angle with x, y, and z axis, right? So with x-axis, it has angle of alpha. With y-axis, it has an angle of beta. With z-axis, it has an angle of gamma, right? So these angles alpha, beta, and gamma gives us the direction of vector A with x, y, and z axis. All right. So using trigonometry, direction cosines are found using this, right? We know we have done geometry and trigonometry, right? So cos alpha equals ax divided by a. Cos beta is ay over a. Cos gamma is az over a, right? If you just do the geometry, you can find out these direction cosines. Okay. All right. And finally, these angles are not independent and they must satisfy the following equation, this equation. We know that this is a rule. Cos square alpha plus cos square beta plus cos square gamma equals 1, right? So that's a rule which the system needs to follow. Okay, so that was about the direction angles which this vector or any vector makes with x, y, and z axis in terms of, we do it in terms of alpha, beta, and gamma. which are the angles which that vector makes with x, y, and z axis, right? Okay, let's move forward. Now, we are good about Cartesian vector, right? Now we know about this I, j, and k system and the Cartesian vectors, right? So now let's focus on the addition of Cartesian vectors. How do we add Cartesian vectors? How in the Cartesian vector space? So once individual vectors are written in Cartesian form, it is easy to add or subtract them. The process is essentially the same as when 2D vectors are added, right? So this is essentially the same process, same method as we did in 2D space. So now we are doing the same in 3D space. So this is how we do it. Fr, which is the resultant vector, equals summation of f, maybe 2 or 4 or 10 or 20 vectors, any number of vectors. The sigma f means summation of all the vectors, right? So summation of fx times I plus summation of fy times j plus summation of fc times k, right? So we'll add up all the x, y, and z components along with I, j, and k notation, right? So that's how we get this fr, which is the resultant vector. Okay. Now, just for an example, if we have a vector A, which is axi plus ayj plus azk, right? Because we are talking about 3D space, so we have x, y, and z components, 3 components of this vector, right? Okay, and we also have a vector B, which is this guy, bxi plus byj plus bzk, right? So we have these 2 vectors. Now we can find a plus b. We can add these 2 vectors. So just add their x and y components and along with I, j, and k notation, right? So that's how we can get a plus b, the addition of the 2 vectors a and b, right? So what we'll get a plus b in this form. Ax plus bx times I plus ay plus by times j plus az plus bz times k. So that's how you'll get the addition of these 2 vectors a and b, right? Or we can subtract these 2 vectors. We can do a minus b. So in that case, just subtract the components, right? So ax minus bx times I plus ay minus by times j plus az minus bz times k, right? So just subtract the b components from the a components, and you get this guy, which is the product of a minus b, right? It's the result of a minus b, not the product. Okay. All right. So that was the theory part of using Cartesian system for 3D space, right? For 3 dimensions, x, y, and z. Now, let's do an example problem just to know more about this Cartesian space in 3D system. Okay, so on the left side on the screen, you can see this figure where you have this hook, and there are 2 forces, F1 and F2, acting on this hook, right? So this is F1, which is 500 pounds. This is F2, which is 800 pounds. So we have these 2 forces acting on this hook. Now, since this is a 3D system, so we have y-axis, we have x-axis, we have z-axis, right? So we have 3 coordinate axes because this is 3D space problem, right? So 2 forces F1 and F2 are applied to the hook. We need to determine the resultant force in Cartesian vector form. Okay, so we know how to do that, right? So we'll just apply the concept which we learned in today's lecture. Okay, all right, so what are the steps? How we go about it? First step is using geometry and trigonometry, write F1 and F2 in Cartesian vector form. Okay, so we'll find out we'll resolve these F1 and F2 into its components, right? And then we'll write those in Cartesian vector form. Then what next? We just need to add the 2 forces by adding x and y components, right? X, y, and z components, all right? Because this is 3D space problem. Okay, all right, so that's how. Now let's move forward. First, let's resolve F1. let's take them on one by one, right? So here we are only talking about F1. Then subsequently we'll talk about F2. So F1 is 500 pounds force with a triangle ratio of 3, 4, and 5. Now let's see how we resolve force F1. So how do we resolve this force? We'll resolve it into X, Y, and Z components. Right? Now, if you look closely, this force F1 is parallel to x-axis, right? Or along x-axis, right? So that's why there's no x component, or x component is 0, right? So F1x is 0 or 0 pounds. Okay, so there's no x component. Now we can resolve this F1 into y and z components, right? So let's do that. F1y equals F1 times 4 by 5, right? So we'll do this and we get F1y as 400 pounds. Okay, all right. Now let's talk about z component. So once we go for the z component, or F1z, we get F1 times 3 by 5. So 500 times 3 by 5, which will give us F1z with a magnitude of 300 pounds, right? So that's how we resolve this force F1 into 3 components, X, Y, and Z components, right? So now we are done with F1. So let's write F1 in Cartesian vector form, right? And also don't forget the units. Okay, so let's write F1 in Cartesian vector form. So this is the force F1, vector F1 in Cartesian vector form, 0i plus 400j plus 300k, right? F1x times I plus F1y times j plus F1z times k, right? And we need to remember that we have to show the units, so pounds. So this is how we write the force F1 in Cartesian vector form. Okay, so now we are done with this force F1 by resolving this force into 3 components and writing this force vector F1 into Cartesian vector form. Okay, let's move forward. Now, next thing is your force F2, which is 800 pounds force at some angle, right? Which is, angles are given. Okay, so we have X, Y, and Z axis, so we need to find F2x, F2y, and F2z. Now, we cannot directly resolve this F2 into X, Y, and Z components, right? Because it's not in any axis direction, right? It's at some angle, right, to all the 3 axes. So what we need to do, we need to resolve this force. First, we'll resolve this. We need to resolve this force 2 times. So first time, once we resolve this force, as shown in this red color, we'll resolve this force F2 into F2z, which is along the z-axis, and F2 dash, which is not in any axis direction. And then second time, once we do the resolution of F2 dash, we'll get F2x and F2y, right? So that's how we need to do this resolution 2 times. Okay, now let's see. Resolve force F2, we'll get F2z, which is along the z-axis or in the direction of z-axis, and we'll get F2 dash, right? So let's see. Let's talk about this F2z. How do you get this F2z? F2z, you'll use this 45-degree angle, which it makes, and we'll find out F2z, which will be F2 times sine of 45. And F2 dash will be F2 times cosine of 45, because we are using this triangle, right? The triangle shown on the figure. Okay, and since F2z is acting downwards towards the negative z-axis, so we'll put a negative sign here, this negative sign. right? Okay, so negative 800 times sine of 45, which will give us negative 680.7 pounds. And again, F2 dash is 800 times cosine of 45, which gives us 420.26 pounds. So this was the first resolution which we did for this F2 to get F2 dash and F2z. Now we need to resolve this F2 dash again to find out F2x and F2y, right? So let's see, let's do that. Okay, so now let's resolve F2 dash. Now F2 dash can be resolved in, because F2 dash makes an angle of 30 degrees with the x-axis, right? So now we can resolve this F2 dash into x and y components. So just use this angle of 30 degrees with the x-axis. So we'll get F2x equals F2 times cosine of 30, which will give us 64.8 pounds as F2x. And F2y is F2 times, or F2 dash times sine of 30, which will give us negative 415.2 pounds. Okay, so in these two steps, now we are done with the resolution of this force F2 into three components, F2x, F2y, and F2z, right? So now we have three components. Now we can write this force F2 into the Cartesian vector system. All right, so F2 equals 64.8, or F2xi plus F2yj plus F2zk, right? So 64.8i, negative 415.2j, and negative 680.7k. So that's how you are done with the resolution of this vector F2 into three components, and writing this vector F2 into Cartesian notation, Cartesian vector form. Okay. Now next is just the adding up of these vectors, right? So we'll get FR, which is the addition of F1 and F2. So F1 plus F2. Now we know that we just need to add X, Y, and Z components, right? So just add X, Y, and Z components. This is your F1, this is your F2. So once you add these X, Y, and Z components, you'll get this. This is your vector FR, right? FR is 64.8i, negative 15.2j, and negative 380.7k. And always don't forget the units. This is compulsive, right? So this is required. So always put the units here. Okay, so this is how we use this Cartesian system in 3D space, three-dimensional space, to resolve the forces into its components, X, Y, and Z components, then writing the force vector, 3D vector, into Cartesian notation, Cartesian vector form, and then adding the vectors, right? Okay, so that's how we are done with this example problem relating to this concept, and we are done with today's lecture, right? Okay, so see you in the next lecture. Thank you.